Hello and an absolute enthusiastic welcome to this Chemistry with SM Explainer. I am so stoked you're here. If you're looking to completely crush your IGCSE or O-level chemistry syllabus, well, you've landed in the exact right spot. Today, we're going on a bit of a trip into the invisible world of matter. We're going to uncover the hidden rules that dictate how particles move, mix, and dissolve all around us. So let's just dive right in.
Okay, I want you to picture something super common. Imagine someone sprays a bottle of perfume all the way across a large room. Within just a couple of minutes, even if you're standing on the complete opposite side, you can smell it, right? But how does that actually work? How on earth do those completely invisible scent particles travel across that empty space to reach your nose without, say, a fan blowing them? And here's a second little mystery for you. If you drop a tiny, dark purple crystal of potassium manganate into a perfectly still glass of water, you don't even need to stir it. Just wait. Over time, that intense purple color will slowly, kind of magically creep outward until the entire glass of water is a perfectly even, pale purple. What invisible forces are pushing those color particles around? Well, that's exactly the core scientific theory we're breaking down today.
Here is our roadmap for this explainer. We're going to hit 1. Diffusion in gases. 2. Diffusion in liquids. 3. Diffusion in solids. 4. Solubility of gases. 5. Real-life connections. And then we'll wrap it all up with a summary and review. Let's go!
All right, kicking things off with Section 1, Diffusion in gases. To solve the mystery of those traveling perfume molecules, we have to nail down the absolute foundational rule of particle movement. The big concept here is diffusion. What is it? Diffusion is simply the movement of particles from an area of high concentration to an area of low concentration. You definitely want to highlight those two exact words in your notes, diffusion and concentration. This is a totally spontaneous process. It happens completely naturally, without any external energy, just because particles naturally want to move down that concentration gradient until they're perfectly evenly distributed. Basically, where there's a huge crowd of them, they naturally want to spread out to where there's more empty space.
If we look right at the IGCSE syllabus, we find the kinetic particle theory. And according to this theory, particles of matter are literally always moving. In a gas, these particles have super high kinetic energy. They're widely spaced out, they're zipping around rapidly, and they're just randomly bouncing off one another in every possible direction. Because of all this insane energy and the huge open spaces between them, diffusion in gases happens really fast.
To really picture this for your exams, let's talk about the classic glass tube experiment. Imagine a really long, sealed glass cylinder. At one end, we stick a cotton ball soaked in concentrated ammonia, which gives off ammonia gas. At the exact same moment, on the opposite end, we place a cotton ball soaked in concentrated hydrochloric acid, and that releases hydrogen chloride gas. Both of these gases start rushing toward the middle of the tube. But here's the cool part. It's actually a race, and they do not meet exactly in the middle.
When the gases finally meet, they react and form a totally visible, white, smoky ring of ammonium chloride. But that ring forms way closer to the hydrogen chloride side. So why does that happen? Well, look at the numbers. The relative molecular mass of ammonia is 17. The mass of hydrogen chloride is 36.5. Ammonia is so much lighter. According to the rules of diffusion, lighter gases act like sprinters. They have a lower mass, so they diffuse way faster and travel much further in the exact same amount of time than those heavier, slower hydrogen chloride molecules.
So let's summarize the absolute must-know rules for gas diffusion. First, lighter gases diffuse faster. The rate of diffusion is inversely related to the molecular mass. Smaller mass equals faster speed. Second, and definitely highlight this key word, temperature. A higher temperature massively increases the diffusion rate. Why? Because heating up a gas gives the particles more kinetic energy, which makes them move way faster and collide much more frequently.
Moving right along to Section 2, diffusion in liquids. So what happens when we lower the kinetic energy, drop the temperature, and pack those particles way closer together? Remember our purple water mystery from the start of the explainer? When you drop potassium manganate into water, it slowly dissolves. The purple particles break off and start to move randomly, bumping into the tightly packed, invisible water molecules. This constant random motion, just endless bumping and shifting, gradually pushes the purple particles away from their crowded high-concentration area around the crystal, out into the pure water, until the color is evenly spread everywhere. This is a brilliant way to see the key difference between our states of matter. You need to be able to contrast gases and liquids for the exam. Yes, diffusion in liquids definitely happens, but it is much, much slower than in gases. Liquid particles just have way less kinetic energy. They move slower, and here's the kicker. They're packed really close together. Because there's so little empty space, the diffusing particles are constantly crashing into the liquid particles, which acts like a giant microscopic traffic jam, slowing down their journey from high to low concentration.
Briefly touching on Section 3, Diffusion in Solids.
For your core chemistry exams, you just need to know that diffusion in solids is incredibly slow, like almost completely negligible. Why? Because solid particles are locked into a super rigid, tightly packed pattern. They just don't have the kinetic energy to break free and slide past one another. They can only sit there and vibrate in place. Honestly, it takes extremely high temperatures, we're talking steel manufacturing or semiconductor baking, for any solid diffusion to actually be noticeable.
All right, on to Section 4, Solubility of Gases.
Let's pivot to a related and super highly tested twist. We've talked about gases spreading in the air, but what happens when gases dissolve directly into liquids? This brings us to another massive keyword, solubility. When we talk about the solubility of gases in water, the rules are actually super specific and honestly kind of counterintuitive. Lock these two rules in your mind right now. First, the solubility of a gas actually decreases as temperature increases. Basically, hot water holds way less gas than cold water. Second, the solubility of a gas increases as pressure increases. Squeezing the gas actually forces more of it to dissolve into the liquid.
Want to know why this matters outside the lab? Look at this number, 5 to 6 parts per million. That is the exact amount of dissolved oxygen fish need in their water to survive and thrive. If the water temperature rises too high, maybe during a crazy hot summer or because of industrial pollution, the solubility of oxygen drops. If that oxygen level dips below 3 ppm, it is super stressful for the fish and it can even be fatal. Temperature literally dictates exactly how much life-saving gas the water can hold. We can also relate solubility right back to your favorite ice-cold soda. Soda manufacturers want that amazing fizzy flavor, right? So they dissolve excess carbon dioxide into flavored water using low temperatures and incredibly high pressure. Then they slap an airtight cap on it to trap that pressure inside. The second you crack open the bottle, you break the seal. The pressure drops instantly, the solubility of the CO2 plummets, and all that trapped gas violently escapes from the water. That escaping gas is exactly what we call the fizz.
Section 5, Real-Life Connections.
Let's bring all this theory back to the real world to really anchor it in your brain. Chemistry isn't just something trapped in a textbook. It's the invisible engine running our daily lives. When you catch a whiff of perfume across a room, you're experiencing gas diffusion firsthand, high kinetic energy particles racing to a lower concentration. When you watch food coloring slowly tinting a glass of water, you're seeing liquid diffusion navigating that microscopic traffic jam. And when you leave your soda out and it goes totally flat, you're just watching gas solubility in action as the CO2 escapes into the air.
And finally, Section 6, Summary and Review. Let's lock it all in. We have crushed a lot of material today. Let's do a rapid-fire recap of the absolute must-know facts for your exam. Number 1. Diffusion is always the movement of particles from an area of high concentration to an area of low concentration. Number 2. It happens way faster in gases than in liquids because of higher kinetic energy and wider particle spacing. Number 3. The rate of diffusion depends heavily on mass. Remember, lighter is faster, and temperature. Hotter is faster. And lastly, gas solubility is totally controlled by temperature and pressure. Just remember the soda. Gases dissolve best in cold, highly pressurized environments. So, that wraps up our explainer on the movement of particles. The next time you smell someone's perfume or crack open a fresh fizzy soda, I want you to ask yourself, what invisible high-speed marathon are these tiny particles running right this very second? If you found this breakdown helpful, make sure to subscribe to Chem Mastery with SM for more easy chemistry lessons. Keep studying hard.